as you go or at the end if you like. And I think that's it. So this is Sarah Millholland. She is a Hubble Fellow at Princeton, and she's going to tell us about short period exoplanets.
All right, thank you. I will share my screen now. All right. Everything look all right?
Looks great.
Okay. Well, thank you so much for having me here today. It's great to have the opportunity to speak with you, and kind of too bad to not be able to be there in person. I had a really great summer in Boulder for an REU during undergrad, so I'm always kind of looking for opportunities to come back and visit. So hopefully someday in the future. So in my work, I'm really motivated by trying to understand the demographics and the diversity of extrasolar planetary systems. So what kind of systems exist in our galaxy and how do they differ from our solar system and why? So to investigate this, I primarily use orbital dynamics and theory to try to investigate the observational patterns that we see. So in this talk, I'm going to focus on the influential role of tides for short period planets. And specifically, I'm going to highlight the surprising role of planetary obliquities or axial tilts in generating strong tides. So, all right, so I think that still kind of one of the most remarkable discoveries in the field of exoplanets thus far is really the realization that roughly half of sun-like stars are accompanied by these close-in small planets with orbital periods ranging from days to months. And I'm really interested in this population because they represent such a large fraction of extrasolar systems, but also because they enable some of the best physical characterization. So this is a graphical representation of systems discovered by the Kepler mission, where the radial coordinate is the logarithmic semi-major axis. And so you can see that this population contrasts really sharply with our solar system, where the inner edge is marked by Mercury's 88-day orbital period. And these close-in planets are also generally a bit larger than Earth, as you can see with this size scaling here. They're frequently in between the sizes of Earth and Neptune. And as you can see with this kind of pie chart style depiction, there's also a fairly large fraction of multi-transiting exoplanetary systems. So I'm primarily going to focus on these types of systems today. So these systems of multi-transiting planets exhibit a lot of interesting structure and regularity. So one of the kind of quintessential examples of these types of systems is the Kepler-11 system, which was discovered back in 2011, hosting at least 6 planets. So the system is really compact and the orbits are extremely circular and flat. So the planets are all kind of in between the sizes of Earth and Neptune, and all of them orbit inside the orbit of Venus, with the inner 5 having fairly uniform spacing of their orbits. So what I mean by structure is that this system has very low complexity. It's almost kind of as architecturally simple as a planetary system could get. And if we look at these same features on the scale of the whole Kepler multi-planet population, we can see that this orbital structure continues. So the systems as a whole have fairly low eccentricities and inclinations on average, as we can see with this heat map of mean eccentricity versus mean inclination. In addition, the distribution of orbital spacings between planets in the same system peaks fairly sharply around a characteristic orbital spacing of about 20 mutual Hill radii. So this kind of, again, sort of signals the preponderance of these fairly highly structured, evenly spaced, and not very complex systems. This structure continues beyond orbits, though, into the physical properties of the planets. So that is, systems or planets within the same system tend to have similar masses and radii as one another. And this, you can call it intra-system uniformity, or peas in a pod is a more kind of catchy way to say it. But this was first pointed out by Weiss et al. 2018, and then our work from 2017. So this is fairly easy to see for the radii on the right, where if you kind of scan your eyes through these various systems, you see that the planet radii tend to have similar radii as their neighbors, more so than they would if you were to just assemble systems randomly from the population. And this depiction also shows the tendency for uniform orbital spacing fairly well in addition. So this is for radii, but if we look at on the left, we can see mass in radii, masses in radii, and where I'm depicting all planets within a given system with the same color and connected by lines. So you can see, again, that systems tend to be clustered on the mass radius plane, that if we were to assemble systems randomly from planets dots in this mass radius plane, we would get a dispersion that is much higher than the dispersion that we see among the real systems. So kind of like so far, it looks like everything is really like straightforward. These systems are really structured in their orbital and physical properties. But it's not entirely so simple. So if we take a closer look, we can contrast this sort of first order structure that we see among these multi-planet systems with some kind of second order architectural anomalies. And so by architecture, I'm referring to kind of the orbital arrangement of planets and their physical properties. And by anomalies, I mean kind of complex deviations from just uniform structure. So there are many examples of this, but I'll just point out kind of a few here. One example is that the occurrence rate in the radius distribution takes on a bimodal shape. And this lower kind of peak of planet radii from about 1 to 1.5 or so Earth radii are now called the super Earths. And those with this larger peak is now known as the sub-Neptunes. Another dichotomy can be seen in the eccentricity distribution, where if we look at the eccentricities of multi-transiting systems, they tend to be a lot smaller eccentricities than those of single transiting systems. Another sort of architectural anomaly we see is that if we look at the period ratios of pairs of planets within the same system, we can see that this distribution of period ratios is fairly smooth overall, except there's these kind of overabundances just wide of the 3:2 and 2:1 period ratios or mean motion resonances. And finally, a last architectural anomaly I want to point to is there's a subset of systems with extremely close in kind of outlier planets that they kind of appear to be separated off from an otherwise uniformly spaced system. So I'm going to talk about a few of these observations today, specifically these bottom two, but all of these kind of interesting architectural anomalies, including ones that I didn't even point towards, require some explanations. And if we can figure these out, then we can better understand planet formation and evolution for these close-in planets. And so I would argue that many, but not all of these architectural anomalies arise from post-formation dynamics. So that is kind of evolution after the initial formation in the protoplanetary disk. And so such dynamics include things like resonance interactions, planet-planet scattering, tidal interactions with their host stars, irradiation-driven effects, so effects due to the strong irradiation they receive, giant impacts, etc. So many different things going on after the system is fully formed. And in this talk, I'm going to focus on the importance of tidal interactions. So tidal interactions are particularly strong for short period planets because of the steep inverse distance dependence of the tidal force. So the magnitude of the tidal force goes as 1 over distance cubed. And so it leads to a pretty significant tidal distortion for close-in planets. That's kind of pretty exaggerated here, but you kind of get the picture. And whenever this tidal bulge is forced to kind of move due to rotational or orbital motion, this leads to dissipation or tidal heating in the planet. And in the equilibrium tide model, the tidal luminosity, or the rate at which this thermal energy is dissipated from the orbital energy, is given by this expression here. where E is the eccentricity and epsilon is the obliquity. So this plot below shows the tidal luminosity as a function of the planet's tidal quality factor, which is kind of a measure of how dissipative the planet is, versus the semi-major axis of the planet. And these dashed lines are contours of the ratio of the tidal luminosity with respect to the incident stellar power. And I'm plotting this just for some kind of fiducial fiducial planet parameters. So we can see that in the very close-in regime, the tidal luminosity can get up to about 1% or so of the incident stellar power. So in this plot, I just used a fixed eccentricity and obliquity, but in order to kind of talk about the dependence of the eccentricity obliquity in the tidal luminosity, it's helpful to kind of put this in a greater context. And so to do that, I sometimes kind of like to point towards one of the best examples of tidal heating that we know of. So this is Io, the innermost moon of the Galilean satellites around Jupiter. And it's the most geologically active body in our solar system due to the really immense amount of tidal heating that it experiences. So Io has such strong tides because it's locked in a resonance with neighboring moons that keep it at a forced eccentricity. And this forced eccentricity means that there are continual changes in the strength and the direction of the tidal force from Jupiter that sort of stretch and squish Io's interior and lead to an immense amount of interior heat deposition. So in addition to eccentricity tides, you can also have obliquity tides. And so imagine now that rather than having a forced eccentricity of its orbit, that Io was forced to maintain a non-zero axial tilt or obliquity. And so now in this case, the orientation of the tidal bulge sort of shifts with respect to Io's equator every orbit. And this leads to similar stresses and strains in its interior, which can lead to tidal heating. So both eccentricity tides and obliquity tides contribute to tidal heating. And here's a look at this again in 2 dimensions. In both of these parameters, where the heat map is the tidal luminosity. And I mentioned earlier that these close-in Kepler planets generally have fairly low eccentricities. And so in this regime, obliquity tides can have a really strong, or like a much stronger effect than eccentricity tides because the eccentricities are so low. However, exoplanet obliquities have kind of been largely ignored in the field thus far, and this is because it was just largely assumed that they were zero, because there was really no reason to think otherwise. And so in this talk, I'm going to give some reasons to think why exoplanet obliquities might matter, and I'll largely be focusing on the role that these non-zero obliquities could play. So for the remainder of the talk, I'm going to propose that tidal interactions, and particularly obliquity tides, could explain several of the architectural anomalies that we see among the short period planet population. And I'm going to discuss 3 specific examples. So the first topic I want to focus on are these so-called ultra-short period planets, which I alluded to a little bit earlier on when I was giving some examples of these architectural anomalies. So the primary question that I want to try to address here is why we see planets with such extreme proximity to their host stars. Extremely close-in planets are particularly peculiar when we think about the fact that planets form in disks, and so they shouldn't be able to form inside the inner edges of these disks. And these inner edges are likely controlled by magnetic truncation, and they're roughly inside about a 1-day period. However, we do see planets inside of 1-day periods, as you can see in this occurrence rate versus period below. And this population inside of 1 day are called the ultra-short period planets, or sometimes the hot Earths. And it's generally agreed that these USPs, as I'll call them, cannot have formed in their present day orbits because of this issue that I mentioned above. And so they must have migrated from larger separations. And so the question is then, how did that happen? So in trying to solve this puzzle, we can kind of try to put together some of the observational clues. One clue is that these USPs are pretty rare, occurring only about 0.5% to 1% of sun-like stars. They're also slightly more common around smaller mass stars than larger stars. And their occurrence decreases with orbital period, as we can see in this occurrence rate plot to the left. And finally, they're also generally pretty small planets, less than 2 Earth radii, as we can see in this radius occurrence plot. And so this means that if they initially had any amount of hydrogen-helium envelopes, they likely lost those envelopes due to intense radiation from the star. So this plot shows all or almost all ultra-short period planets in multi-transiting systems. And so we notice these USPs are in red, and we notice that they typically have multiple close-in co-transiting planets. And statistical arguments have further shown that these USPs almost always have companion planets with periods less than 50 days, even if they're not always co-transiting. So another key feature that we can see here is that these USPs tend to have fairly large period ratios with respect to their nearest neighbors. And these period ratios are generally a lot larger than the typical separations that we see among these close-in planets. So this is a suggestion then that these planets could have started at kind of the inner edge of such systems with more typical separations, and then moved inwards. So these observational properties, specifically regarding the larger separations with respect to the nearest neighbors, points towards a formation channel via orbital decay driven by tidal dissipation. And as I discussed earlier, one way that tides from the star can lead to dissipation in the planet is if there is a planetary obliquity or axial tilt between the spin axis of the planet and its orbital axis. And one way to maintain this obliquity in the face of tidal dissipation is through a configuration called a Cassini state, which is something that I'll describe in more detail soon. So here I'm going to describe this process by which a USP can be produced from the innermost edge of a close-in system. And I've named this process Obliquity-Driven tidal runaway. And so it can be described in 3 component steps that I will go through in detail. And the first is entry or capture of the planet into a Cassini state with a non-zero obliquity. So to illustrate how this works, imagine having just a 2-planet system with a slight mutual inclination between the orbits that I'm kind of exaggerating in this diagram. And we want to understand how the obliquities of the planets evolve. So due to secular or kind of long-term average interactions between the 2 planetary orbits, both of the orbits are precessing around the total angular momentum vector. So this kind of looks like this. And in a low eccentricity and low inclination regime, this frequency, which we'll call G, just depends on the masses and the semi-major axes of the planets. In addition, there's another precession, and this is due to, so torques from the star onto the oblate figures of the planets cause their spin axes to precess around their respective orbit normals. And this spin axis precession we can label alpha. And so the comparison of these 2 important frequencies, G and alpha, dictates the resulting dynamics. So in this precessing orbit frame, Cassini states are what are named the equilibrium positions of the spin vector in this uniformly precessing orbit frame. So basically, they are the points in this frame in which the planet's spin vector is fixed. And this condition can be written with this expression here, where G and alpha are the frequencies I just defined, epsilon is the obliquity, and I is the inclination. And so there are up to 4 different Cassini equilibrium states, depending on the ratio of this orbital precession frequency to the spin precession frequency, G to alpha. And an important point is that only states 1 and 2 are stable in the presence of tides. So on the right panel, this is a closer look at these two stable states where I'm showing them for different values of the inclination, where so these different opacity lines correspond to different inclinations. So the key idea then is that for close-in planets, tidal dissipation will rapidly force the obliquity to equilibrate in either state 1 or state 2. And so if this ratio G over alpha is out here, kind of beyond unity, then state 2 is the only state that the planet can occupy. And so the obliquity can be forced to be at least the inclination or greater than that. Whoops, sorry about that. And so when this obliquity is non-zero, then this leads to dissipation in the planet, which leads to orbital decay. And orbital decay tends to decrease this ratio G over alpha, which further increases the obliquity and leads to even more orbital decay. So just to kind of reiterate this picture, the tidal equilibria of the obliquities that they will be forced to occupy are non-zero. And so sustained obliquity-driven tidal dissipation becomes inevitable. So as I've kind of already alluded to, once this obliquity is in this non-zero state, tidal dissipation will lead to orbital decay. And the rate of this orbital decay induced by tidal dissipation can be calculated in the equilibrium tides framework, which I'm showing here for some typical planetary properties as a function of the orbital period and the obliquity. So here is the 1 billion year contour line. And so the key point to kind of see here is that if the planet begins with a small enough initial orbital period and an enhanced obliquity, then it will decay to even shorter orbital periods where the rate of decay becomes even faster. And so this begins kind of a runaway orbital decay process. So this process wouldn't work if the orbital decay just continued at a runaway rate indefinitely, because the USP would crash into its star and then we wouldn't see it today. So something has to kind of stall this orbital decay, and this is Cassini state breaking. So Cassini state breaking is essentially the limit at which the tides become too strong to maintain the obliquity. And as the orbit decays and moves up this Cassini state 2 branch, the obliquity becomes too large to be stable due to tides, and it breaks out and damps back down to state 1, which is a much smaller but still non-zero obliquity. So on the right here, I'm showing a couple examples of this with different initial orbital periods. And so you can see, and this is the color bar is the obliquity of the planet. So you can see that the rate of decay eventually goes runaway, and the obliquity gets really high really quickly, and it eventually breaks out of state 2, goes back down to state 1. And at this point, it's stalled at a much shorter orbital period. And because this runaway kind of happens so fast, we're not really likely to see this in the process happening in real time. But there is one example of the system that might be currently undergoing this, which I could talk about more later if you're interested. So I've kind of just outlined how this mechanism can take a short period planet at the inner edge of a multiple planet system and become a USP. But what is the region of planetary parameter space that is susceptible to this? So here I'm plotting as a function of the mass and the initial semi-major axis of the planet. These shaded regions show kind of where the planet is susceptible to becoming a USP. I don't have time to go into the details of how this calculation works, but something that is interesting is that if we compare these parameter space regions for different stellar masses, we can see that there is slightly more space so more susceptible to becoming a USP for smaller stellar masses. And this is interesting that this tends to go in the same direction of the observations that have indicated that USPs are more common around smaller mass stars. So this is sort of an intriguing comparison to the observations here. we find that it agrees well with other observed trends of the USPs, such as their period ratios and inclinations, but I don't really have time to talk about all of those here. But so as far as kind of testing this theory of USP production with further observations, we have a couple of things that we can do. One thing would be to obtain some better constraints on the eccentricities of planets or systems that host USPs, which would be either through radial velocities or kind of stability arguments. And this is to sort of verify that eccentricity tides do not contribute significantly to the USP orbital migration. And second, I kind of didn't talk about this in detail either, but another sort of prediction of this work is that USP orbits will tend to be aligned with the stellar spin axis, which I'm trying to depict with this black vector, whereas their companions will tend to be a little bit misaligned. And so further observations of the stellar obliquity could help check this. So I kind of want to move on now to the next topic. And so just as the ultra short period planet problem sort of stemmed from some anomalies in the distribution of the orbital periods, there are also some kind of peculiarities when we look at the distribution of orbital period ratios. And so this problem still pertains to these close-in multi-planet systems, but I'm not going to be focusing on the extremely short period planets anymore. So we can see this problem when we look at the distribution of orbital periods of which I'm showing here for Kepler systems. So the x-axis is the distribution, the ratio of the outer planet to the inner planet for pairs of planets within the same multiple planet system. And a feature that has been noticed as significant in this distribution for some time is that there's a little bit of an overabundance just wide of the 3:2 and 2:1 period ratios. It's a little bit hard to see here, but if we zoom in near this 2:1, we can see that there's a clear excess just wide of the exact 2:1 ratio and a deficit inside of that. So several authors have shown that if the planets can first get captured into mean motion resonances through initial migration in the protoplanetary disk while they're still forming, and then subsequently, after the disk goes away, undergo tidal evolution, then this tidal evolution will cause planets to move from an exact mean motion resonance to slightly wide of the resonance in the direction that we see this offset. But there's a problem with this picture, and that is that it requires a significant source of extra dissipation, or in other words, that the planets have to be a lot more efficient at dissipating tidal energy than it's thought that they should be. So we're kind of in need of some extra source of dissipation that is a couple order of magnitude effect. And so maybe you can anticipate where I'm going to go to hypothesize for this extra source of dissipation. But so in this study from last year, we showed that if we account for the extra dissipation that could arise from non-zero planetary obliquities, then that several order of magnitude extra effect could be the amount that we need to move planets wide of the exact resonances by the amount that we see. However, this solution requires that these planets frequently have non-negligible obliquities. And so what is there to suggest that they actually do? So it's not that the planets just can have high obliquities, but we actually expect them to from obliquity excitation from a dynamical resonance called a secular spin orbit resonance. And so the key idea to this is realizing that these high obliquities Cassini states can be generated in two separate ways. The first is if this G over alpha frequency ratio evolves through orbital decay, as I was talking about for the USPs. But another way is if this G over alpha ratio evolves through means other than orbital decay, such as other evolutionary factors at play in the early part of the system's lifetime. So we call this mechanism resonant excitation because these two G and alpha frequencies, the orbit precession and the spin precession frequencies, are evolving and becoming commensurable, kind of crossing through unity here. And so this is called a secular spin orbit resonance, and it's sort of just an instance of a Cassini state, but just different language. This mechanism is not new. Interestingly, it is thought to have generated Saturn's 27-degree obliquity due to basically the orbital precession of the motion, the component of orbital precession from Neptune becoming resonant with Saturn's spin axis precession frequency. Okay, so just to kind of reiterate here, if the planet begins with this G over alpha frequency ratio out here, and this frequency ratio evolves, then the planet can get excited to large obliquities. And so we found a really interesting feature of these close-in Kepler planets that they're highly susceptible to these spin orbit resonances due to some frequency commensurabilities. So this is because their typical orbital precession frequencies, G, as I'm showing with this histogram, tend to have really similar values to their spin axis precession frequencies, as I'm showing with these dashed histograms. So therefore, as the system kind of is evolving early on and the G and alpha frequencies become commensurable, these systems can evolve into these resonant encounters that make large planet obliquities. So thus, these high obliquities should be kind of a frequent occurrence for these close-in planets. So this has kind of been a qualitative discussion of this topic so far. So to kind of give you a better sense of how this works and how these planets can get captured into these high obliquity states, I'm going to show you an example of a spin orbit evolution simulation showing what happens to a typical young planetary system as it evolves and it encounters these resonances. So the key with this is that in order for these planets to encounter these mean motion resonances in the first place, they need to be undergoing some at least small amount of migration in the protoplanetary disk to get captured into the mean motion resonances. And as this migration happens, it changes the G and alpha, both of these G and alpha frequencies, and they can lead to the spin orbit resonances. So in this top plot, I'm showing the obliquity evolution of two planets as a function of time, and in the bottom plot, I'm showing the precession periods. So if we focus on this plot first, the blue and green here are showing the periods of the spin axis precession of the two planets, and the purple is showing the period of the orbital precession. So you can see that the inner planet first encounters this resonance where the spin precession period becomes equal with the orbital precession period, and this kind of excites the obliquity. But the obliquity can only be captured in the resonance from the other direction because of some fine details. And this, so you can see that it here encounters the resonance again, at which point the obliquity gets excited to a value of around 50 degrees or so. And this obliquity stops evolving when the G and alpha frequencies stop changing. And so then it's kind of just captured in this high obliquity state that it will maintain indefinitely, even in the presence of this tidal interactions. So that kind of example simulation is just demonstrating what we think might be happening for at least some subset of these planets near mean motion resonances. There are, however, some kind of additional interesting layers to this, and that is because of some of the details that happen when we're near these 2:1 and 3:2 period ratios. Our hypothesis predicts that planets wide of these resonances should have slightly larger obliquities than planets just inside of the resonance. But so now, if these planets are experiencing tidal heating on a stronger magnitude than these due to their larger obliquities, then we would expect that this intensified heat deposition within their interiors could puff up their atmospheres and lead to some amount of radius inflation. And so we kind of predict that these planets should have larger radii than these just inside that have smaller obliquities. So this kind of brings me to the third and final architectural anomaly that I want to point out. And this basically kind of follows from this line of reasoning to address why some planets might appear to have larger radii than we would naively expect them to. So we're kind of expanding away from talking about the tidal effects on planetary orbits and thinking about what these tides could do to their interiors. So first, I just kind of want to follow this line of reasoning from before to examine whether planets wide of these mean motion resonances do indeed have larger radii compared to those just inside. And so to do this, I'm going to look at how the planet radii compare across the entire period ratio distribution. So here's just kind of a coarsely binned depiction of the period ratio distribution, where I'm plotting it with bins of width 0.05. And I'm going to look at just adjacent bins in this distribution. So here are just two randomly selected adjacent bins. And then I'm going to look at the mean planet radius in a given period ratio bin. So it's kind of a lot going on, but hopefully it makes some sense. So look at the mean planet radius here and compare it to the mean planet radius in just an adjacent bin. So this is a little bit of a mathematical description of what I'm trying to describe here. And then I want to look at this across this entire period ratio distribution. So here's the result of that calculation, where on the y-axis is the ratio of the mean radii in adjacent period ratio bins, and I'm plotting this as a function of the period ratio. So the purple circles are indicating all places where this ratio of radii is greater than about 2 sigma enhanced over unity. So we can see that the only places that this happens at are at the 3:2 and 2:1 mean motion resonances, although we also see a little bit of enhancement near these other first order resonances as well. So kind of the takeaway here is at least an intriguing it's an intriguing observation that these planets wide of mean motion resonances seem to have anomalously large radii. So with this observation then of these larger radii for planets wide of mean motion resonances, which we have kind of already predicted to have large obliquities, the natural next thing to do is to examine the question of whether the tidal heating hypothesis offers a consistent explanation. So to address this, I looked at a sub-Neptune evolutionary planet model, which was developed by Chen and Rogers 2016, which essentially just assumes a heavy element core with a hydrogen-helium envelope. And this envelope is evolved using the 1D stellar evolution code called MESA, which mostly is used to model stars, but can also look at planetary envelopes as well. And my modification to this model was just to include extra heating inside the planet that we would expect to be there if obliquity tidal heating is operating in the planet. Okay, so to get a sense of then like how much does these obliquity tides result in any amount of radius inflation of the planet, I did kind of just a large Monte Carlo suite of planet models where I was varying the planet mass, the amount of mass in the hydrogen helium envelope, the strength of the stellar radiation, the strength of the obliquity tides, etc. Well, actually, no, just those 4 key parameters. And so here's the result of this kind of Monte Carlo suite of simulations, where I'm looking at just the degree of radius inflation that we get from tides. So on the y-axis is the ratio of a planet radius when you include tides in the model to the planet radius in a tides-free model. And I'm plotting it as a function of the ratio of the tidal luminosity with respect to the incident stellar power. So it's clear that when this ratio of tidal luminosity to incident stellar power is big enough, like bigger than about 10 to the -5, then tides can pretty substantially inflate the planetary atmosphere up to about a factor of 2 times its size compared to if we were just ignoring the effects of tides. So very broadly speaking then, the simulation results here are plausibly consistent with this observational result in the sense that we can attain planetary radius inflation by up to a factor of 2, which is sort of the same order of magnitude as the amount of inflation that we see for these planets wide of resonances. But I think more modeling work would be necessary to understand whether this is truly consistent with the magnitude of radius inflation we're seeing here. Okay, so given this sort of really interesting effect of tides on the overall planet radius of sub-Neptunes, we might wonder whether this could also explain other observations of the close-in planets. And so sort of the last thing that I want to mention pretty briefly is a separate group of planets that we think might have been inflated due to tides. And this is a group of planets which we call sub-Saturns, which are planets in the 4 to 8 Earth radii regime that previous works had thought contained about 50% of their mass in their envelope and 50% of their mass in their core. And there are about roughly 10 or so planets that have been discovered with this apparent balance of mass. But planets like this pose a problem because they shouldn't exist according to the theory of core-accretion, which represents the dominant paradigm of planet formation for gas-rich planets. So this theory holds that if a solid core forms before the dissipation of the protoplanetary disk, then this core will accrete gas from the disk at a rate set by the internal cooling. And when the mass in the envelope is roughly equal with the mass in the core, then the envelope kind of hydrodynamically collapses under its own self-gravity and undergoes a phase of runaway gas accretion that transforms it into like a Jovian-sized planet. And so this theory predicts that we shouldn't find any planets with a balance of 50% core and 50% envelope mass. So the fact that we have found at least 10 or so that with planets at this threshold has been a bit of a problem. So we proposed a solution that many of these sub-Saturns are not actually as gas-rich as their masses and radii suggest, but rather their envelopes just look really large because they've been inflated through tidal heating, mainly from eccentricity tides, but also potentially from obliquity tides. So I want to illustrate this quickly with an example for K2-19b, which is a short period planet on about an 8-day orbital period with an observed eccentricity of about 0.2. And when standard core envelope structural models were used that ignored tidal heating, it was inferred that the envelope mass fraction was about in the range of 40 to 50%, so pretty close to this 50% runaway threshold. But if we include tidal heating in the structural model of the planet, we find this kind of posterior parameter regime in the tidal quality factor of the planet and the envelope mass fraction. So we have assumed here that the eccentricity is fixed at the observed 0.2 eccentricity, but we have can look at different values of the obliquity, which are these different colors. So basically, the planet is less envelope rich than it originally seemed after we account for the fact that its envelope has been inflated a bit from tidal heating. And the more dissipative the planet is, so lower Q factors, the smaller envelope that we need to match the observed radius of the planet. So we could see that the actual envelope size mass fraction of the planet could be as low as about 5 to 10%, depending on the obliquity and the tidal quality factor. So this kind of resolves this tension for this previous estimate, which was much closer to 50%. So this K2-19 example sort of raised questions about the degree to which other sub-Saturns could have been shaped by tidal inflation. And so I looked at the full population of sub-Saturns with fairly good mass and radius estimates. And so this plot is comparing the envelope fraction estimates that we get when we ignore tidal heating in the model to when we include the effects of tidal heating on the planet's atmosphere. So we see that there are pretty significant differences when if we ignore tides versus include it. And so this is sort of a histogram of the comparisons when again we ignore tides versus we have them in the model. So the sort of takeaway here is that tidal heating really is an important factor that we need to account for in these planet structural models. And sub-Saturns could really just be sort of sub-Neptunes that have been inflated more than normal and not necessarily a separate class of planets. Okay, so just wrapping up in the last just minute or so, I just wanted to talk really briefly about how we can test some of these theories more. As far as obliquity tides, the most obvious way would be to try to observe some planetary obliquities directly. And this is still really challenging, but there are some techniques that I think should prove fruitful going forwards. And for example, signatures of non-zero obliquities could feasibly be seen in phase curves of planetary orbits, which are when we essentially look at the total integrated light across the planet's whole orbit. So we kind of already tested this out a little bit with this planet core-2b, which had some unusual properties that I won't go into, but which these unusual properties could be reconciled if the planet does have non-zero obliquity. But I think this method needs some more testing to see how it can apply. But another proposed technique for measuring the obliquity are secondary eclipse mapping, which is basically looking at the brightness map or creating a brightness map of the planet as it is occulted, so as it passes behind the star. And this is proposed to be doable with James Webb for planets of sufficiently large radius. I think the most promising technique, though, for James Webb will be measuring the deviations of the transit light curve compared to what we would expect the transit to be if it was spherical, if the planet was spherical versus if it was slightly oblate. And this can give you some residuals that kind of look like this. And this offers you constraints on both the oblateness of the planet and the obliquity. So this is a promising thing to try with James Webb. And finally, there was a technique for directly image, so much further planets, but this can also be used to constrain the obliquity, and it was used actually for the first time in a paper published earlier this year. So kind of in short, I think that there are some promising methods for trying to obtain some more direct constraints on planetary obliquities in the future, which can help us test these tidal theories that we've put forward. So just to sum up now, these close-in planetary systems are full of really interesting structure, but also a lot of kind of surprises that have required explanations. And I think that the dynamics of tides and maybe obliquity tides can help explain some of these features, both in the orbits of the planets, as I talked about for ultra-short period planets and these pileups wide of resonances, but also in the interior structures of planets when we think about what the effect of tidal heating does to their atmospheres. So going forward, I think it should be really interesting to keep examining these architectures and just better understand the dynamics and the diversity of these short period planets. So I said a lot of stuff, and I look forward to your questions. Thanks.